In Part 3 of Lecture 8, we will discuss paging and segmentation. The problem with the memory management strategies that we have discussed so far is that they either lead to extensive fragmentation problems or they require that we spend a lot of time compacting memory. If processes could be loaded into non-contiguous areas of memory, we wouldn't have this problem. This is exactly what paging is all about. Logical memory remains contiguous and is composed of pages of memory, all of which are of a fixed size. These are loaded into blocks of physical memory of the same fixed size called frames, but these frames do not have to be contiguous. As we will see shortly, there is a certain amount of overhead associated with paging, but it is well worth the price that we pay because external fragmentation is completely eliminated. Logical addresses consist of a page number and a displacement, the number of bytes from the beginning of the page. Physical addresses consist of a frame number and a displacement. The displacements in both cases are exactly the same. All that differs is that logical addresses include page numbers and physical addresses include frame numbers. Every page number must have a corresponding frame number. That is how we can translate logical addresses into physical addresses. We'll see in a moment exactly how this translation is done. Paging works because in the course of performing every memory access, we will look up the page number in the page table. The register holding the address, or the address register, to be accessed receives a copy of the displacement directly from the logical address. The page number is then looked up in the page table, and the corresponding frame number is then loaded into the address register. The page table is an array of frame numbers. If the page number is n, the computer goes to the nth entry in the array. This is done directly, so it's fairly fast. It has to be. We'll do this every time we fetch or store anything in main memory. When you look at the logical and physical memory layouts, you won't see a resemblance. However, if you look at the page table, it gives away the relationship. It tells you that page 0 is stored in frame 1. Page 1 is stored in frame 2. Page 2 is stored in frame 0. Page 4 is stored in frame 4. And page 4 is stored in frame 6. You'll notice that contiguous frames do not necessarily hold consecutive pages, and that the pages are not at all in contiguous frames. That's all right. The only thing that's important is that there is no unique frame that holds a particular page number for our process. Imagine that the operating system is ready to load a new process into memory. It will load page 0 into the first frame on the free frame list, page 1 into the next frame on the free frame list, and so on. When the new process is completely loaded into memory, you'll see that two processes coexist in memory, each with their pages stored in their own set of frames. The most important question, of course, is how do you implement the page table? The quickest way of accessing a page table is if it is stored in registers, high-speed memory locations, built into the processor itself. This is how it was handled on the PDP-11, a popular mini-computer built by the Digital Equipment Corporation. The page number consists of 3 bytes, which meant that the page table could have up to 8 entries. The displacement consisted of 16 bits, meaning that each page could hold 8 kilobytes. The page number indicated which register in the page table contained the frame number. Using registers made the paging process work quickly. The only problem is that once the page table grows larger, it becomes more and more expensive to design a computer this way. Once the page table exceeds 256 entries, it is no longer practical to implement it this way. Most modern computers can have page tables that are quite large, with hundreds of thousands or even millions of entries. This makes it prohibitively expensive to use registers to implement a page table. We have to use main memory. We'll use the page table base register to tell the memory management unit where the page table begins. The page number serves as an offset, indicating how many bytes from the beginning of the table we have to go to find the frame number. The only problem is that it's impossibly slow for the sheer number of memory accesses that we will have to look up. Looking up a page table in memory turns every memory access into 2 memory accesses, one for the page table entry and one for the operand or instruction. What we need is a trick that keeps it from looking up the same thing repeatedly. And that's where associative registers come into play. When we need to determine a physical address from a logical address, we look up the page number in associative memory as well as in the page table. In associative memory, we look up our page number in all the registers simultaneously. If there's a hit, if we find it there, we will get the frame number. If not, we wait for the value to come from the page table, which also stores it in an associative register together with the frame number. Maybe this memory access took longer, but the next time we look up this page, we'll find it much more quickly. The hit rate that we get, the percentage of memory accesses that are found in the associative registers, determines how quickly we can access memory when our page table is implemented this way. You'll see the term TLB on the slide. This is an acronym for Translation Look-Aside Buffer, the other name used for the associative registers in which we store the most recently used page table entries. Paging actually makes it easier to implement memory protection. This is accomplished by adding protection bits to the page table entries. In the diagram on the left, the one marked A, you'll see that the page table includes an extra bit that indicates whether the page number is valid or invalid. Any logical address in an instruction that accesses a page table entry marked invalid will generate a memory protection error. Similarly, we can use these extra bits to indicate if the page is read-only or if write permission is also granted. This is shown in the middle diagram marked B. If a user program tried to write on a read-only page, this would signal a memory protection error. We can even extend the idea to marked pages as execute only, as you'll see in the diagram on the right side marked C. But this leaves one remaining question. Processes rarely use all the memory available to them. This would leave page table entries which may not be in use. We can also limit the scope of the page table by using a page table length register, or PTLR, which keeps track of the actual size of the page table. Any reference beyond the entry indicated by the PTLR would cause a memory protection error. In any case, it's clear that paging provides us with several ways of protecting memory, as long as the necessary hardware support is there. Computers now use longer addresses than older computers used. The reason is that as addresses get longer, there is a larger set of values that can be expressed and that can serve as addresses, and therefore more memory can be used on these computers. While a 16-bit address can provide enough addresses for 64 kilobytes, a 20-bit address can provide enough addresses for 1 megabyte, and a 32-bit address can have enough addresses for 4 gigabytes, something that we have long since started using. The problem is that page tables get so large that it is very difficult to ensure that we can store them in contiguous memory locations. The answer to the problem is to apply paging here as well and page the page table. In the example that you see here, addresses are divided into 3 fields. The first one specifies which page of the page table we are using. The second for the entry in that page of the page table, and the third for the displacement. This requires an extra memory access, but one is necessary if we are going to work with such a large memory space. The extra memory access is not so much of a big concern, because we will store many of the entries in the TLB, the associative registers that we discussed before, and because it is not so slow compared to virtual memory, which we will discuss soon. The Digital Equipment Corporation, VAX, was the first 32-bit mini-computer. It paged the page table, although the organization was a little different from what we saw before. The page table was divided into 4 sections, each of which had 2 to the 21st power entries, with 4 bytes per entry. Remember, it was a 32-bit machine. Each page table section was 8 megabytes in size. It's not surprising that the VAX used separate process page tables. Most computers have separate page tables for every process. The problem is that each process could, in theory, have millions of page table entries, especially if it is using 32-bit addressing, which is fairly common these days. The problem is that it takes up a lot of space, which may not even be used. Most of these addresses may be invalid, and it ties up enormous amounts of memory for no good reason. We can get around this by inverting the page table. The page table stores the process identification number and the page number, and we search for it. The search gives us an offset from the top of the page table, which is our frame number. Instead of using the page number as an offset to get us directly to the frame number, we do a linear search to get the offset. While this takes much longer than a conventional page table search, it requires much less memory because invalid page numbers need no entry. In effect, we are trading a speedy search for savings in memory. Paging seems to have some overhead. We need to access memory twice as often to look things up in the page table first. And of course, we then need memory to store the page table. But we'll see that it can also save resources for us. Imagine two users both using the same program. That means that the computer doesn't need 2 copies of it in memory if they can share the page. Paging and our ability to mark pages as read-only or execute-only makes this possible. Processes 1 and 2 both are running the same program, which is stored in frames 2, 1, 6, and 4. Both programs have read-only access to these frames. But pages 4 and 5 are different. These are their data pages. As a result, these processes are using 8 pages of memory instead of 12. Users do not typically think of memory as a linear array of locations. In most cases, they think of it as a collection of discrete modules, including things such as user-written procedures, library routines, the stack, the main program, global data, and so on. It would be helpful if our model of memory reflected this view of memory. So the logical organization of memory and its physical implementation had a direct relationship, one that aided implementation instead of hindering it. This is essentially what segmentation is about. A segment is a unit of memory which handles a module like the ones that I just mentioned. In a segmented system, an address consists of a segment and a displacement from the beginning of the segment. The segment number would then be replaced by a frame number. It looks a bit like paging with 2 significant differences. Segments are not necessarily the same size. Pages are by necessity the same length. Segments are organized around the program. Pages depend much more on how the program is divided into units of equal size. The basic implementation is very close to that of a paged memory system, except we must keep track of how long each segment is. This was not a concern in the case of paging, because the length of a page was preset. The segment number is used to take you directly to the appropriate entry in the segment table, where we will get the limit of the segment, or how large an offset it can have, and the base address. If the displacement is within range, we then add it to the segment's base address and get a physical address. If not, we get an address protection error. You'll notice that I use the terms offset and displacement interchangeably. The two terms mean the same thing, and which one is used often depends on which system you're talking about. You'll notice also that this implementation has the segment table in memory, with its starting location stored in the STBR, the segment table base register. This assumes that the segment table is too large to be stored in registers. This is not always the case. The Intel 8088 and 8086 worked with segmented memory and used 4 registers to hold the base addresses for its 4 segments: the code, data, stack, and extra segments. This scheme worked because there were only 4 segments. Once the table grows significantly in size, implementing this in registers becomes unwieldy. Any memory management scheme requires us to consider how we will protect the areas of memory used by the operating system and the various processes running on a computer. As with paging, segmentation is helpful in this regard. We can use the various segments assigned to a process to represent the various parts of a program, such as the code and the data. It also makes it easier to check the indices of an array if we contain it in a given segment. If the index times the number of bytes per data item is greater than the upper limit of an array segment, we know that we have exceeded the size of the array. Another advantage of such a setup is that we can share data and code by allowing more than one process to access its segment table. Memory allocation in a segmented memory system works similarly to the way it works in a paged system, but it has a few differences. External fragmentation can be an issue because segments are not all the same size. Compaction can alleviate the problem, but this gets back to where we were in MVT, where processes loading and unloading can cause fragmentation problems to be alleviated by compaction. Of course, we could work with smaller segment sizes, but this eventually gets us back to paging. Paging and segmentation both offer advantages. Using them together can work better in some instances. One approach, which Multics took, was to page memory segments. The segment numbers were used to get a page number for the segment. It was the segment's page table which contained the frame numbers instead of the segment table itself. While the scheme is a little more complex, with an extra step in getting the physical address, it made it easier to manage segments, which would otherwise be 64 megabytes long. OS/2 version 2, which used the 32-bit mode of the Intel 386 processors, used a similar scheme. The page table was divided into separate pages. The first 10 bits pointed to the entry in the page table directory. The second 10 bits pointed to the entry in the appropriate page table. This allowed the page table to be stored in areas of memory which were not contiguous, making it easier to implement.